Welcome back to the stream. Last week we left off with this where we implemented function calls, so we were able to write a very basic example that computes Fibonacci numbers. Of course, the code looks a bit weird because we don't have parameters at the moment, so we have to pass the parameter as a global variable, and we also don't have any if statement, so we have to use like the expression, conditional expression to do all the choices. This is both things are going to change today, so we're implementing parameters and if statements, and then see how long this will take, maybe while loops and things like that. So I did a bit of work between streams. I cleaned up a lot of the code. There were some bugs that I needed to fix in the supporting libraries and things like that. So I did a cleanup there. And I also did performance optimization to Love. So previously, we were in a benchmark, compared it to compiling with Clang and then running it. And I believe Love took about 1.8 seconds to interpret, to generate code and interpret it, whereas Clang took only about 300 milliseconds total to both compile it and run the program. And the reason for that, a bunch of indirect access to a global variable access was pretty expensive. So I did some optimizations in Love where it's just similar to the existing optimization for local variables. Instead of having to compute the address, validating it, and then dereferencing it, it hardcodes a valid address to a global variable as an instruction. So it knows that the address is valid because it's a global, it lives throughout the entire lifetime of the program. So it's able to hardcode that and remember that. And which means then some other constant following stuff. But with both optimizations combined, if we run the benchmark now, I should have compiled first. It's a lot faster. Like it's over 1 second faster than last week, simply by doing this bytecode optimization. So it's only about 3 times as slow as Clang. If you look at the rough overview of the performance data, this load global value is still dominating. And the reason for that is you don't have to understand the assembly code, but essentially to access a global, we first need to, so this is a memory access that reads the index of the global variable. And then we are doing a memory access here. This accesses per process table of all memory allocations. And then we're indexing into that to get the actual address of the global variable, which we can then dereference. So we have to go like 3 memory accesses until we finally get the value of the global variable, compared to getting a local variable. So for example, here, to load a local value, we just get the index of the local value, and then we dereference the stack frame, instead of having to go through the table. So this is saves an extra memory access, which makes it a lot faster. So when we implement parameters, we can benefit from this optimization because parameters are also implemented as locals. Yeah, but before we can get started with that, there is one feature we don't support at the moment, which is when we move the function here and provide forward declaration. It can't handle that. So let's fix that. And the reason it can't handle that is quite obvious. When we pass a declaration, we have a to-do right here. So at this point, we need to create declaration node for a function and then later add a body into it. So let's call this decl. Okay, so we want to create a function declarator type. We're doing the same here. Since we're only having int, we're hardcoding the return type as int. And then we create the function. So we create a function decl. What does the constructor take? Function decl, the name and the type. So name, there's a function get name. name, the type. Then we create the node. And oh right, then I also need to provide the location and the symbol of the name, and then add that back to the list of declarators. Okay, we needed to do here verify and compute correct return type. Yeah, let's add this here. So for example, we could have a forward declaration that looks like so, where this would be a function that returns function type. The error message says this returns a function that returns an int, but we can't return a function directly, so we need to catch that error, but we don't. But this is something that we'll add once we add a proper type system into our language. Okay, so now we are creating the declaration, which means that when we now see the second one, we are complaining that we have a duplicate global declaration. Because we haven't told it yet that when you see a definition, you look for a matching declaration first and fulfill that. So here we are creating a declaration, the same to do about the return type, which means that as soon as we get the name, we check whether we might already have a function. So this is at global scope. So we do state global symbols. We look for the name. It's not null pointer. Then we need to verify that its return type and arguments and so on matches with the declaration. We'll just not do that for now. Verify that definition matches declaration. Because we currently don't have much anything, right? It's a return type and we only have int, so the return type has to be int, so we don't need to verify anything here. But then, yeah, so let's leave this blank. Otherwise, we need to create a new one. From the declaration, pass the body, and set its name. And trycast, this has to be a function decal. And that should be it. We're getting a segmentation fault, so that's nice. Oh, right, this is a null pointer. Right. Auto existing decal. So if we have an existing decal, then we cast it. Otherwise, this is not pointed directly. And then we're doing that. Which node is already linked in the tree? So we are pushing back. The function decal is already, right, it's already part of the thing. So we need to, it's already, so the issue here is that we are reusing the existing declaration and returning it. And then when you create the translation unit, it attempts to insert that into the list of declarations that are owned by the translation unit, but it is already part of the translation unit. So we shouldn't return it. What happens if we just, so is linked in tree? If it is, then we just return null pointer, otherwise we return the declaration. This is probably going to crash because we can't handle, yeah. Because concat attempts to do. So we want to return a declaration, but we don't want to add it to the list. I'm just going to hack this locally here. So in my local copy, where we're doing push front of a node, I'm going to be really... Where do we crash? Right here. So I'm just going to hack and say that if the node is null pointer, then we return. And likewise do that here. So now it should just work, and I'll fix that in the library properly after the stream. Okay, so it works, and we still running. So now we are creating, you know that even though the definition comes after main in the tree, it comes before main, because when we pass the definition, we modify the existing node instead of adding a new one. So that's nice. Let me see what happens if I declare a global variable called fib and a function. Then we are getting a duplicate global declaration. Nice. And we're getting that because we're checking when we pass a global declaration. When we're passing a global declaration, we only reach this point if the existing declaration is a function declaration. Otherwise, it is null pointer, and we're creating a new one, and then here we're complaining about the existing one. So it just works out nice. So support forward declarations. Next up, we want to pass parameters. I always forget where the file is. So we want to pass parameters. The standard has this complex grammars for declarators, where we've got a function declarator. Currently, we're only passing empty parents, but we can pass an optional parameter type list. And this parameter type list is a parameter list, and then we've got optionally followed by the 3 dots to indicate a variadic function. We're not worrying about those for a long time because I need to do a lot of work to support them in Love. But if we ignore that, then parameter list is just a comma-separated list of parameter declarations, where a parameter declaration is a regular declaration, or an abstract one, which just means it's the one without name. So we can, like the parameters, we can write int a, int b, and this is then the regular parameter declaration. And or we can do that, and now the first one is an abstract parameter because it doesn't have a name. I will also not worry about unnamed ones for now, just to keep it simple, and then we will add them later on. Okay, so a function can have parameters, which means we need to modify the function type to also have a list of parameters. So let's add to the constructor, let's add an alias for type list of type. And then in the function type, we've got the type list parameters and the child list after return type parameters. Let's make this typo. Okay. So now we're complaining about the constructor when we create them here, because we don't provide any types. So let's just say that we're always having an empty type list. Okay, so we're still compiling. When we pass a function declarator, a function declarator also has a list of types. So a function declarator has a child one and then type lists. So this also has a list of declarators. This is annoying. This has a list of. So this has a list of parameters as its child, not a list of declarators. This is a bit annoying because we're dealing in a sort of... yeah, okay. So I need to add a parameter to the tree first. So variable decl. Let's copy it now. A parameter declaration. So parameter decl has a name and a type. And right now they are identical to variables, but eventually we will add initializers to variables, and parameters don't have initializers. Also, a variable can be declared external or static, and parameters can't. So they will diverge over time, which is why I'm creating a separate tab. So I'm creating a parameter decor. Parameter decor. Parameter decor. Okay. Still compiles. Now we want to our function declarator has list of types. Let me add an alias for that. So parameter list is a list of parameter decals, and here we are having a parameter list, parameters, 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 parameters. I don't need to getter, just add them locally. Okay, parameter list, parameters. Now it will complain that we don't provide a parameter list when we pass a function declarator, which makes sense because we're not parsing anything. So a parameter decal consists of declaration specifiers followed by declarator. So essentially they look just like declaration, except that we don't allow a single one. So we're currently only having type specifiers. And then we pass the declarator for the parameter. And okay. And when we get a value, we get a callback that will return a parameter declaration given the compiler state, the type specifier, which is just the type at the moment, and we know that this is always int, and then we getting a declarator. And then we want to create a new parameter declaration. So this has to be a named decal at the moment. So let's because a parameter can't be a function, right? So we have to let's just cast this down. Let's just do a let's just abort if we don't have one. Doesn't matter. Worry about proper error messages because we have to handle like pointer declarators at some point eventually anyway, and then we can clean this up. But for now we just downcast that to a named declarator, and then we specify that we have get the location from the named declarator. Oh, I don't actually need that. So I can just do this, get name decal, and then the name also gives us a location. So we use that. So the location of the name, the symbol of the name, then the type, I'm assuming, where to create variables. Variables, name, symbol, type. Right, name, symbol, type. And then a function declarator. At this point, we are parsing a list terminated by a closing paren of optional parameters separated by comma. Okay, this is a bit of a mouthful, This means that we need to provide support. So let's try to make this properly and write a parameter list production, which parses it also consumes the closing paren, which is a bit weird, but that's okay. And then the value is simply a list of, is it simply a parameter list? Okay, close it here, and then I can say here plus parameter list, and then I can just say that here when we get the function declarator we get the location, and then we also get a parameter list. So zero parameter list params, which I can then add right here. Okay, that's still pass, and we're still passing because we haven't actually written any parameters yet in our code. So let's see what happens when we do that. So let's say pip takes n as parameters. And then we've got, yeah, essentially we are passing it, but we're not doing anything with the parameters yet. So this hasn't changed, because when we create a function declaration, we need to set parameters. So we need to, oh, we're actually creating a wrong type. That is, notice how the type of a function decl is int as opposed to function type of int. It doesn't matter because we are just not looking at the type at all at the moment. So let's do that properly. So here we need to create a function type. Function type, no location. I will overhaul the entire type creation at some point anyway, and to use like some sort of interning so we don't have to create the same type over and over again. So a function type, return type is the int type, and the parameters are coming from and then this is a function type, and you're actually complaining now, right? Because we don't, at this point when we only, to get the type, we don't care about the names of the parameters. We only care about their type. So we have to create a new list of type list, parameter types, and for each in decl parameters, we clone the type, but we can do that. We hardcode the type to be int. This is so silly. And then add that to the parameter type. Clone the type of param. Right, so we would normally copy the type over from the parameter to our parameter type list, but we're not, right, it's, we don't have the types at the moment. Okay, parameter types. This is the type of the function. This is great. And now our function type, it's a bit unreadable, but like this is the return type and this is the argument. So that is correct. If we don't have a forward declaration, so at this point we need to do the same thing. So we need to just copy this code. So the function decl parameter types. of the declarator so let's just again hardcode that this is a function declarator, and then do that. Okay. And again, we are not right. We would need to generate an error because we are passing a parameter here but not there, but we don't do that. We're about that next week probably, but still this worked properly. Okay, so now we've added parameters to functions, but we are not. This doesn't affect Codegen in any way at the moment. So in order to have it affect Codegen, what we need to do, go to Codegen. And first of all, the way this works is... actually, let me do something else first. So we're having the parameters as part of the type, but we also want to have the parameters part of the declarations, because the type will only give us the type and does not give us the name, and we need the name to do name lookup and stuff. So we will also add the parameter list into our AST. So after the type, we are having the parameters, which is a bit annoying. Yeah, after the type, we're having the parameters, and then we will later inject the block between type and parameters here, which means that to get the parameters, so if we need to query whether they have a block here, bool is definition. If it is a definition, so it's a definition if we have, I don't actually know how to check that. And my language server crashed, so that didn't help. So function declar. Alright, so this is child after, which let's just say has body false, body true. So if it's a definition, it's a definition if it has a body. And then if we have a body, then we return node range of type parameter declar, starting at the child after the body and ending at the last child. This returns the pointer. I want to create an iterator. So children, can I get an iterator from pointer? So I want to get an iterator. Is the type exposed here? The type. Okay, this is really annoying. I really need a better API for that. So I'm trying to compute an iterator to get to the first parameter. We're storing the parameters. I'm doing it the other way around. That's easier. So I'm remembering pointer to the last parameter, right? That is so to the last parameter. If we have a parameter, then the last parameter is the last parameter. Okay. Then this is, so if we're having a last parameter, it is the child after the last parameter, otherwise it's the node after the type. And so we're inserting here as well. So if we're having a parameter, otherwise it's the type, and then here begin is child after the type. Okay. I'm seeing that there's a lot of API missing, so I have to do a lot of stuff manually. Otherwise, this is the last param. So I need to get the iterator type, children iterator. So make node range parameter decor iterator from pointer begin iterator from pointer end. So the namespace name here. Otherwise, we're returning parameter decor iterator. Okay, that's a lot more complexity than I would have liked. I need to cast them. So I need to add proper APIs for that to do that. Need to fix a bug there. Okay, and now it complains in the function. That is an error that we can handle because I want to pass the parameters. Decor parameters. And in the second place, we're creating function. Now it's right here. Decor parameters. So now we've finally added parameters to our tree, right? So we've got the function type and then we've got the parameter. Good. Let's do Codegen. So when we generate a function, what we essentially want to do is we want to create local variables for every parameter. So for auto param in decor parameters, we create a new variable for them. Build local, native layer allow runtime value to do types other than int, and add parameters to the thing. Local variables dot insert param decor gadget as well. Add a const here. Okay, and now we are creating local storage. We're not actually creating local storage, probably because that thing is wrong. So my folder was probably broken. This was the wrong target. Let's debug what's going on. So we wanted to add parameters, but we didn't. So let's see exactly. Begin is the child after, and end is 3e8. Oh, right. This has to be inclusive. This is the child after the last part. And okay, so we have now created extra local storage for our parameter, which is good. The next thing is we need to update the signature of the function. So currently the function still takes 0 values, and we need to add how many parameters it has. I don't think I have a size method, so let's just do parameter count. This is the distance, decal, parameters begin, decal, parameters end, and we truncate them for now to unit 8. So we've got a hard limit of 256 parameters. And now a bunch of errors will happen, because we need to do a bunch of things. So our entry block now also takes. So the way parameter passing in Lauf works is the stack, right? It's a stack-based language. So when we, for example, evaluate an expression, we push its value onto the stack. And when we call a function that takes n parameters, those n parameters are on the stack already. So the entry block takes however many parameters the function takes as inputs. Right? So that's the first thing. And now the issue is because we've pushed them onto the stack, but we still only have a single return value. So they remain on the stack, which means that we now return 2 things because we push everything on top. So we need to consume the parameters. And we need to consume them by storing them into the corresponding variable that we've created. So we map parameters to variables. We can't leave them on the stack directly because we can only use things on the stack once, right? When we try to use this, they are popped from the stack. So if we want to use the parameter multiple times, we need to store it in a place where it remains. Also, we can't take the address of variable while it's on this temporary stack, only if it's a local variable. So we need to, when we enter the function, parameters on the stack, pop them all, store them in local variables. This is also very similar to what Clang does. So the Clang generates assembly. The first thing it does, it stores all the arguments that are passed in register, it stores them onto the stack. And we're doing the same thing here. So I want the address of the variable we just created. Store and store them. So now our main function, first thing it does, it stores the value on top of the stack, which is the parameter, into the first local variable, which is the one we've created for our parameter. This, unfortunately, we are doing this in exactly the wrong order if you have multiple parameters. So, for example, 2 parameters, A and B, the stack will look like so. And then we're creating, then we're storing them. Then we are first storing B into the variable for A, and then we're storing A into the variable for B. So we need to iterate the parameters in reverse to match the way they're pushed onto the stack. And we can't iterate in reverse. So let's just temporarily create a vector of parameters. And since we're creating that anyway, we can also use its size as the parameter count. So let's do that. Params push back param. Then the parameter count is params with size. Now I need to walk that twice. I need to include vector. And then we can iterate the vector in reverse. Reverse end. We create variables for all parameters and store the value into them. Since parameters have been pushed onto the stack and are thus popped in reverse, we need to iterate in reverse order. Okay, so it hasn't changed anything for a single, obviously, but now doing the right thing. And let's actually, yeah, let's keep it that way. Okay, so now we can pass parameters to a function, and this all works. However, I'm very surprised actually, because when we're calling it, we're calling the function. So our Fibonacci function now takes one argument, but we're calling it without any arguments. And because the way the code is generated, it does an indirect call where it does a one-time check of the number of arguments. This is just easier. That's just the way we've implemented it, which means that at one time we get an error because the function address points to a function of invalid signature. So we've implemented parameters in function declarations, but we haven't yet implemented calls. Implement parameters in function declarations. So we need to implement calls, and for that, with arguments in that case. And for that, we need to, again, update the AST. So when we have a function call expression, this now takes an expression list of arguments. So expression list, unlinked node list for expressions. And our function call expression takes an expression list of arguments, which we just insert after the function, insert the arguments. Okay, and we don't need to, yeah, that's the beauty. Okay, so now when we create a function call, we also need to pass arguments. So what does the standard say about expressions? Postfix expression takes an argument expression list, which is an argument expression, like a comma separated list of argument expression. And what is an argument? Oh no, assignment expression, and an assignment expression. So a comma separated list of arguments. And an assignment expression is, right, so an assignment expression essentially is not the top level expression, because the top level expression would be a comma operator, but obviously we can't use a comma expression in a function argument list, because this would then be passed differently. So what's the nice way of doing that here? If I just say that when we do a function call here at this point, pass a list of expressions. It will then pass comma, like pass everything as a single comma expression instead of having multiple arguments. But that is, yeah, that's not nice. So I need to say that I want to pass a different kind of. This is annoying. Okay, so I have to restructure the way we're parsing things. So let me just, when we create the call, for now we will just say, where do we create the call? Right here. I will just say now arguments and change the way the parser works. And change them with the parser works so we can pass in argument expression. So let's say this is an assignment expression, which means that we no longer pass comma. Operation, it's assignment. And then an expression. Is essentially what it says right here. An expression is a comma-separated list of expressions. So a list of assignment expression separated by comma. So we this is a bit annoying. So if we pass it as a list, we will get like a list of things, but we don't want to create a list of things. We want to create like nested comma expressions as we did before. So let's actually also make this an expression production where the atom is an assignment expression and the only operation is a postfix op whose operator sequenced op comma, its operand is DSL atom, and then we need only need the overload for the text, the sequenced one right here. And this isn't called, right, trailing underscore. Why are you complaining about the thing that this is? All right, I need to forward declare expression here. So callback for the expression grammar. What are the arguments? Do you happen to tell me that? You don't. So what's going on here? Oh wait, this isn't a postfix operator. This is an, was it left or right associative? It's, what is, say for plus? So plus is left associative, which means we have the same thing on the left. So we're having the same thing on the left, so it's left associative. Okay, so it's an left associative infix operator. Okay, so we're still parsing them, which means that we can now add them properly. So at this point, we want to pass, we do the same thing similar to we did with the parameter. So we have a parameter list, copy that over, turn it into an argument list, which is a list of assignment expression, and produces an expression list. We need to recurse. And then in the postfix operator here, we are parsing argument list, which means that in the call, right here, we are also getting an argument list, which we are adding to the call. Right, this is expression list. Okay. Of course, aren't actually using it yet. So let's complain that when we create the function, that we have the matching number of arguments, right? So for that, I need the type of the function. So try cast. So this has to be a function type, right? Else our not calling a function, but like some other thing. So if it's a function type, the type and number of arguments has to match. Currently, the only type we are really supporting is int, so the type will always match. So let's just say and matching that the count matches. Count parameters. So the arguments begin and argument count error prompt mismatched argument count. Okay, so now we need to add parameter access to the function type. Parameters right, it's essentially the same code. So I will add some shortcut to dry it so we don't have to write the same logic here. Child after the type and children and type. Return type. And now we're getting a bunch of errors here because we're not actually calling a function. Wait, what? Really? What are we calling instead? Oh, okay. So we're getting errors that we're not calling a function. Let's generate a proper error message first and then fix that. So state.logger.log diagnostic error call expression is not a function. So we want an annotation. The secondary annotation is at the location of the thing that we are calling. Do I have convenience method to get a location? I have from the as that thing. State.as location of. This is actually primary location. So now we're getting errors that the called expression is not a function, which is of course nonsense because it is a function, but the issue is that in the identifier expression we're hard-coding the type to int, but it's not necessarily int. So essentially, this is really annoying. So I really need to copy the type of the declaration. So let's write a simple function that copies a type. So let's say it here. So type, clone type, type, type. So we want to visit all possible nodes. So if we have a built-in type, we return state as create a new built-in type, ignoring location for types for now, type kind. And if you're having a function type, then we are iterating over all the parameters. Typed it, param types, push back, clone type, state, param, and state, create, function type, with clone type, state, type, return type, and the param types. All right, this is a const one, which makes sense, but that's fine. So we can also create const here, const here. And then we cast them to types. That's actually put it here. Okay. So now an identifier expression can actually copy the type. State. Decal type. This is called clone type. So now those errors have disappeared because we're now having the correct type of the identifier expression. For example, if we see in the AST here, where do we actually call things? Function call expression. The type of the identifier expression is a function type. Of course, the error at this point is that we are not actually matching the arguments. So let's create a nice error method for that. Log error mismatched invalid argument count for function call. And just do the same thing. So we're now generating nice errors for well, nicer errors. Ideally, we would also like say what the argument, no, let's just say what the argument count is for a function with %d parameters. And this is size t, so argument count, parameter count. Right, invalid arguments count 0 for function with one parameter. Okay. Since we are now, let's do that later. Okay, so let's actually fix the calls and say that here we want 35, here we want n-1, and here we want n-2. Okay, now we're compiling again, but we're getting the next build error. So we're getting a build error because when we do Codegen for a call expression, I'm assuming we're not pushing the arguments. Right. Right, when we are calling it, we need to actually get the signature. Okay, so this is a bit tricky. We need to know how many arguments to push. Which means that we need to let's write a convenience function to the AST for a function call expression. Oh, wait, no, this we have this information because it's encoded in the type. Function type. So this is the expression function type argument count. Oh, do I have expression not arguments? Function call expression. And okay, so let's do that over the type. So the function type has parameters. And we know at this point we can, because we've had type checked, if we reach this point, we know that this is a function type. So this is a function type. Function type. This is a function type, and it means that where do we generate the call? We are still not pushing any arguments onto the stack, which is weird. Oh, yeah, I see what the issue is. That is very interesting. So the issue here is that is really funny, actually. Hang on, let me disable an optimization so we can more clearly see what's going on here. So the code that we're generating, right, now we're back. For function call, is, so for example, this is the first function call. We want to push the address of our function, which is fib, and then we are pushing its argument, which is in this case the local variable at offset 8. So this is where n-1 is stored, and then we're doing a call. However, the signature specifies that we first need to push all the arguments and then the function. So we need to push them in the different order. So we first need to push its argument, and then we need to push the function that we're calling. And I wonder whether we can just, yeah, we should be able to just say this. So after the type comes the arguments. So we just change the iteration order. Although this is then annoying to access. Yeah, let's just do a little hack here. So we want to modify the stack so that the value that's at stack index argument count is at the front. So now we are pushing the address of the function, pushing its arguments, and then we are moving the address to the very top of the stack, and then we continue. And I wonder whether you're now still able to constant fold that. If I just enable constant folding here again. Unfortunately not. Okay, that's something I'll do off camera. Okay, so now we are generating correct code for functions and function calls, but we're not actually using the argument yet. So let's just see what happens when I do that. So now we don't have a global n, which means that name lookup should find the local one, except it doesn't. Because we are nowhere currently saying it in the compiler, do we add a parameter to the symbol table. So, for example, when we create a decal statement, we add them all to the symbol table. But when we do a global definition of a function, then we need to add all the parameters to the symbol table. In fn. So in the function declaration, all the parameters, insert new decal, state of local symbols, the parameter, local scope. And we're having a const correctness issue. Let me just copy that for now. Clean that up later. So now, okay. Name lookup appears to have found them because we're no longer generating an error, but Codegen doesn't handle something. So we want an identifier expression. Ah, right. Actually, no. It should be inserted into the one. So we've got expression. This is in scope? No, this is not on scope. So we should reach this point. Let me just debug everything. So. Oh, right. Okay. So the issue here is that we're having an identifier expression that does not refer to a variable declaration or a function declaration, but to a parameter declaration. So param decal, cast it to parameter decal. And then we know that this has to be a local variable because it can't be global by definition. Push the value of the parameter onto the stack. And now we need to update the exact same code in assignment, which again is something that I should merge somehow right here. Where we want the address of the parameter on the stack. Wait, this is also not a parameter tagger? I want to look up the parameter tagger. And here I want to look up the parameter tagger. Okay. And it appears to work. Let's actually see what happens when whether it's still correct. So let's just print pip35. This is the correct, it's roughly the correct value. Okay. So this means we can then clean up a bunch of things. -1 plus n-2. Okay, that worked great. And now let's do performance. Let's see what happens to our performance now that we're using parameters instead of global variables. This should become faster, but you never know. It became slower. Okay. Well, roughly the same. Clang just became a lot faster. Okay. That's a bit disappointing. That's really a bit disappointing. I know why it is. Okay, let's commit because we've implemented parameters. Yeah. Implement arguments in function calls. So the issue here is that we are generating indirect calls. Because we are pushing the address, we are pushing its value, not here. We are pushing the address, we are pushing the value, we are subtracting 2, we're moving things around, we're performing a call. And this can no longer be constant folded into a perfect compile time call, which means that we have to do a verification of the function address. And the reason we need to swap them around is because we're generating them in the wrong order. So let's just generate them in the correct order, which is that we need to manually visit. Did I call this child visitor? In the other ones, visitor. Visitor, you need to put node kind. Push each argument onto the stack. Auto arg in arguments. We visit each argument evaluated. Push the address of the function onto the stack. Function. Call the function. And of course I need to increment the argument count here. And I again need to copy code that looks something like this. So child after the function until the end. And this, let's type expression. And now why are we still doing an indirect call? It should have fused those two together into one direct one. It's not doing that, so let me see what's going on here. So we're getting the address. The address is not a compile time That is really odd. But it's no longer fusing those two together. It should fuse the function address and the call indirect into a single call, which saves a bunch of runtime validation. But it's not doing that, and it did do that before. Yeah, since we are not doing statements today anyway, since we had the issue with all the container stuff, so let me see whether I can find the issue or whether I have to do that off camera. So generating the address of a function. So what do we push on the V stack? A constant. Right, this is correct. We're then doing a bunch of steps. Let me set the correct breakpoint in Codegen when we generate, when we go here. This is a constant. I'm popping them in the wrong order. Right? Yeah, so we have to pop the function first, and then we pop them. Okay. So now it has fused those together, so we push the address and then we do an indirect call, has been optimized into we doing a call. Let me see whether this affected the performance. It did. Drastically. So now, sadly, Clang also became faster when we removed global variables, but the performance has gotten a lot better since we're doing that, which is really cool. Are there any hotspots now? Yeah. So now the actual hotspots, they do actual work. So we need to do a bunch of recursive calls. We need to call a bunch of built-ins. We need to load them. We need to do panic subtraction and so on. Okay. So push function call values in correct order. This enables constant folding in love to convert the indirect call into direct call. Okay. Sadly, we can't get to statements today, so we will continue on next week. There we will add statements so we can start writing loops and things and see what happens to the performance then. Thanks for stopping by, and until then.